To give you like a bit of background about me, as said in the intro, I work for NVIDIA. I work on a couple of different open source kind of groups. One is RAPIDS, and one is Dask. Like my main focus is about taking like GPU accelerated data science tools, PyData libraries, and running those kind of anywhere people who want to run those. So whether that's on the cloud, whether that's on an HPC, using whatever stack people like. So there's kind of a theme that'll come up throughout that, through this talk. But the main thing I want to talk about today is kind of taking an application of scaling out some large computational problem onto the cloud and kind of talking about, something topical, I guess. So I want to talk a bit about LLM data preprocessing. So like it's very common to, for LLM practitioners to start with data sets like Common Crawl or, the Wikipedia dumps or archives, set of papers. And there's like a whole bunch of pre-processing that we have to do to those. Like these files come in different formats. They're kind of organized in different ways. There's kind of a lot of unusable stuff in there. There's lots of duplicates and things. And so one of the first things we need to do is kind of download this data, get it in the right format, clean it up, do the like data engineering stuff, basically. And so like a reasonably common pipeline for doing this, it kind of follows this path, and this is taken from a blog post that I'm going to reference like throughout. I've put it in the like resources tab in the AirMeet thing. So if you want to go and find the links to these blog posts, you can click those in the resources. They'll also be kind of throughout the slides and again at the end. But when you're working with these data sets, the first thing you need to do is download those data sets somewhere, whether that's into like object storage on the cloud or onto some local cluster. You do all of the text extraction and pull it out into a format that you want to work with. You then need to go through, clean the data, deduplicate the text, do quality filtering, do all sorts of other bits and pieces before you can actually work with that data. And so I kind of want to highlight this tool that's being worked on by another group adjacent to RAPIDS within NVIDIA called NeMo. And they're building lots of tools around natural language processing. And one of the things that they came out with recently is this tool called NeMo Data Curator. So this is a library that will help you download these data sets, clean them, format them, deduplicate them, all of that kind of stuff. So you can go over to like the NVIDIA documentation and learn more about NeMo and what's going on there. But in this talk, I kind of want to talk about like the PyData stack that's being used underneath all of this and the open source libraries that we work on within RAPIDS that have been built together to solve this problem. And to just kind of highlight why, the group did a bunch of kind of benchmarking of the effect of doing data preparation and data cleaning on kind of the accuracy of the model that's trained. And so one of the things I wanted to pick out here, as you can see, one of the biggest improvements in downstream accuracy here is the deduplication of the data, right? So going through all of the different files in these data sets and trying to remove files that are, extremely similar, not 100% similar. I mean, we definitely want to remove things that are 100% similar, but removing things that are like 99% the same, we see a good uplift in downstream performance. But actually doing that on these data sets is quite a large kind of challenge. And so we use a bunch of different libraries to kind of build up this workflow that we need to run. So the first kind of set of things that I want to talk about is RAPIDS. Now this is like kind of the group that I work in within NVIDIA, and you can go and find us on GitHub. We have like a GitHub org. It's github.com/rapidsi, and it's got a whole bunch of kind of open source Python libraries that are GPU accelerated, and these kind of fit into the PyData ecosystem. So if you're already familiar with libraries like NumPy or Pandas or scikit-learn or NetworkX or kind of the staples of the data science community, you'll find within RAPIDS these kind of drop-in replacements that accelerate those libraries. Right? So if you like Pandas, you can go and try cuDF. If you like scikit-learn, you can go and try QML. If you like NetworkX, you can try cuGraph, etc. Kind of all of these libraries are kind of re-engineered from the ground up, using CUDA and using GPU acceleration. But like the Python API that's presented at the top is kind of the familiar PyData libraries that we're kind of all used to today. But we get some awesome speed ups from doing this, right? Rewriting that low level code to kind of parallelize on GPUs, we can get some awesome improvements. We can see that like one machine with 16 GPUs in is more powerful than like 100 machines with CPUs in. We can kind of run through these kind of data frame, data engineering operations with cuDF and other libraries. So this is kind of what Rapids is focusing on, is taking these things that you would normally do in pandas or NumPy or scikit-learn and kind of accelerating that with GPUs, kind of moving the scope of the GPU beyond model training. You know, like we see GPU benefits in PyTorch and XGBoost and TensorFlow and all these things today, but like also accelerating all the other parts of the pipeline. It's kind of what we're going after with Rapids. Now, if you want to like learn any more about this, or if this is interesting, I can highly recommend one of my colleagues, Ashwin, is giving a talk later about this new library we released recently called QDF.pandas, which is a plugin for pandas that means that you can just accelerate your existing pandas code. You don't even have to convert it over to QDF or do any migration at all. You just import the plugin at the top of your notebook or the top of your script. And the library will kind of switch out, it will opportunistically switch out pandas where it thinks there's some benefit. So you can kind of get zero code change GPU acceleration for all of your existing pandas workflows that you already have today. So go and check out Ashwin's talk. He'll talk a bit about kind of the performance gains we're seeing, but this, the kind of stuff we're seeing with this is taking a pandas workload and, you know, rivaling kind of the best of breed libraries that we're seeing coming out today, like DuckDB and Polars, but without having to rewrite anything, without having to learn any new APIs. You just add a GPU, add this plugin, and your pandas code is going to go 50 to 130 times faster. So yeah, go and check this talk out. It's a bit later on today. But all of these libraries are kind of pretty popular within the community already. We have lots of existing users, lots of people working on and contributing to these libraries and seeing this benefit of CUDA and GPU acceleration within their Python kind of PyData world. So there's like a bunch of material about this already. If you want to learn more about how folks are using these things, go and see, you know, some of the talks like this one. Spotify gave a great talk at NVIDIA's GTC conference about how they're using the Rapids stack to accelerate their model evaluation. But there's like loads of other talks about this, online about how folks are going and using Rapids. So if you want to learn more about exactly the details of Rapids, then go and check those out. But once we start thinking about, okay, I want to accelerate my code on my machine, but in order to work through one of these really big data sets, I'm going to need lots of machines, right? I'm going to need to deploy some kind of cluster on the cloud. I'm going to need to scale out my workload onto that cluster so that I can get through. You know, these are like multi-terabyte data sets, and you know, we're not going to be able to get through that even on, you know, a server full of GPUs. We're going to want many machines to work through data sets of this scale. So let's talk a little bit about what it takes to deploy Rapids on the cloud, and how we go about that. So one of the core libraries we use in this stack is a library called Dask. If you're familiar with the PyData ecosystem, you may have come across this already. Dask is this kind of general purpose Python library for parallelizing out your work. Dask allows you to kind of write custom parallel code, or we have existing collections that also mimic NumPy, Pandas, scikit-learn APIs to scale out. And so this is super useful if you just have a laptop with multiple CPU cores in and you want to scale out your work beyond the GIL and kind of beyond what you can do with libraries like multiprocessing, something that feels a bit more kind of native to what you're doing. But then you can kind of go beyond that to scale to very large clusters and supercomputers. So the way that we do this within Dask is we take a data structure like a NumPy array or a Pandas data frame, and we have like a Dask equivalent of that. So we have like a Dask array or a Dask data frame, and these are kind of chunked, partitioned flavors of those APIs. So if you look at like a Dask data frame, it's made up of many partitions, and each of those partitions is a Pandas data frame. And so we can kind of swap chunks in and out of memory. We can do out of core processing, and we can distribute this work out onto the, you know, a cluster of some kind. And because we're talking about pandas, and because you've got libraries like QDF and QDF.pandas that are these like drop-in replacements for pandas, we can bring in this GPU acceleration into Dask. So we can get this kind of scale-out nature of Dask, where we break up our workload and run it on many cores or many machines. We can then add the GPU acceleration to that as well, so that we can then break up our workload and run it across many GPUs in many machines on like a large GPU cluster. And the way that we do this within Dask is we have these kind of high-level APIs that mimic these kind of PyData APIs. They break up the data structures into chunks. They also kind of have these parallel algorithms that replace, you know, pandas, numpy.mean or something. Like we have like a map reduce style mean operation within Dask that will give you the same result. But because we've broken this out into a task graph, we can have all these individual tasks assigned to different cores or different GPUs. And we have like a distributed scheduler within Dask, which allows you to, you run the scheduler, you run a bunch of workers on a bunch of machines, and then you connect a client in your notebook or in your Python script. These are all kind of things you could just import and instantiate, and they'll all connect together. And then when you run your code, it will kind of generate this task graph, pass the task graph to the scheduler. The scheduler will distribute all of these tasks onto the workers, and they'll start chugging through it very, very quickly. And some of the things that people really love about Dask is that we try and visualize and represent what's going on to you. So if you have this large, chunked array, kind of in your notebook, you can see, okay, this is the shape and size and dimensionality of my array. This is the size of it. This is how big each chunk is. And this, as I'm going to run an operation like mean, this is how the shape of my computation is going to look. And then we also have a dashboard that shows like what are the workers doing, what tasks are being run at the moment, what's taking the time. Because sometimes when you run these workloads, if they take a very long time, it's nice to be able to go in and get an insight into what's going on within your cluster. So being able to mix Rapids and Dask together means that we have to think about how do we deploy kind of GPU clusters on the cloud with Dask running so that we can come and use this as an end user. How do I actually get all of this? So we put a lot of effort over the last year in Rapids into a Rapids deployment documentation website. The links here is docs.rapids.ai/deployment. And then there's kind of loads of different pages in here that talk about, here's how to set up a GPU Dask cluster on SageMaker. Here's how to set it up on Vertex AI. Here's how to set it up on Azure ML. Or if you want to use Kubernetes to kind of abstract away the platform underneath, you can use Kubernetes. There's also kind of lots of managed services out there like Coiled or Databricks that you can go and kind of run these things on as well. And so this documentation will walk through, how do I install the libraries? How do I start the Dask cluster? How do I get the Jupyter environment? How do I kind of get going with all of this? And then we have a load of like end-to-end workflow examples of, kind of showing, given some selection of these tools, right? Everybody's got a different stack, right? Every organization has made a choice about who they're going to buy from and which cloud they're going to use and which services they like. But as long as you can get a GPU there, we want you to be able to use Rapids there. So we have these kind of workflow examples that, okay, I've got data in S3, I want to use SageMaker, I want to scale out with EKS, I want, whatever your opinionated stack is. And then we have some example notebooks that's like, here's how to deploy that and then do hyperparameter optimization, or here's how to deploy that and then do some data pre-processing. So if you're interested in any of this, go and check out that documentation. Now, in order to run this kind of large deduplication workload that we want to do for this, pre-training these LLMs, we can, choose Kubernetes maybe as one approach to this, saying, okay, I want some GPUs to run through this work. I'm going to deploy them on some cloud by creating a Kubernetes cluster. I'm then going to install Dask. We have a Dask operator kind of plug-in for Kubernetes, which lets you create Dask clusters nicely on Kubernetes. And then we're going to use Rapids, the Rapids libraries on top of that. So just to kind of illustrate, we can do this quite quickly. Say I'm going to choose Google Cloud for my Kubernetes cluster. I can run like one command that will create a Kubernetes cluster with some GPUs. All the other clouds have kind of got a rough equivalent of this. I'm then going to go and install kind of the NVIDIA plugins for this so that the Kubernetes cluster is aware of the GPUs. I can then come in and install the Dask operator, which makes the Kubernetes cluster aware of Dask as a concept and kind of be able to create Dask clusters. And then we can kind of list our Dask clusters and create them. So like we have a nice little one-liner for deploying Rapids onto this using the Dask Kubernetes Gen cluster command line tool, which kind of generates all the specs for you and everything. But you can say, okay, I want to use the Rapids Docker container that we publish, which has got all of these libraries and Jupyter and everything else you could want in it. I'm going to deploy that as a cluster. I'm going to ask for each, the notebook, the scheduler, and each worker in my cluster to have one GPU. And that, I specify I want -- Jupyter. I want this to have Jupyter. So this is my front end, and I can come in. I don't need to have a GPU in my, I can work on a MacBook. I don't need a GPU. I can run this on the cloud and kind of work in Jupyter in this environment. And this is a great way for us to do this kind of pre-processing work scaled out on the cloud. We can turn on all the auto scaling and all those kind of features if we want, so that when we're working in our notebook, we're just taking up a small amount of resource. And then when we run our run our pre-processing job, it will kind of scale out, add nodes, and we're only billed for what we need in that time. But like that's one approach that we could take to deploying Rapids and kind of getting these tools in our hands. We have documentation on that site for all sorts of different platforms, kind of every service you could think of in the different cloud providers. And if you're interested in this stuff and you don't see your preferred provider here, go and open an issue on the repo and kind of say, and we can go and fill in another documentation page there. So once we're at this point, right, and we've deployed our RAPIDS Dask cluster onto our, Kubernetes in this example, but once we've deployed this somewhere, how do we actually go through this workload? How do we deduplicate these large data sets? So one of the first things we want to do is just kind of think about this operation. We need to take every document in a data set, like a Wikipedia dump, and we need to compare that document to every other document within that data set, because we want to see how similar they are and then discard any duplicates. But that is, that's an all-to-all operation. That's a big operation. If we've got an extremely large multi-terabyte data set made up of trillions of tiny files, doing an all-to-all comparison is really a big thing to do. So one of the first things we can do is try and group our documents together using some hashing, locality sensitive hashing, so that we're going to generate like a 32-byte hash for each file, and files that are kind of similar in structure and everything will get a similar hash. And because we're working with so many files, we could just generate a hash for each file, and then we'll get lots and lots of files that end up with the same hash. And we can kind of use that to bucket our files and say, okay, we're going to deduplicate. We're going to first kind of bin them into these buckets using like minhash. And then we're going to then only do the deduplication within those buckets. So this first cut allows us to come in and kind of reduce our problem a little bit, because this is still a gigantic problem. So the next thing we're going to need to do, once we've got these buckets of files, we're going to need to come up with all of the comparisons we want to do. So we'll go through every file within each bucket and kind of put together a data frame of pairs, right? I've got file X and file Y in bucket Z. They need to be compared to each other and compared to the other file in bucket Z, and next file, or whatever. So we end up generating this big data frame that just shows all of the pairs, right? All of the buckets, all of the pairs. But we can do this with Dask, so that we end up with this very large data frame that kind of describes our problem, right? It describes all the different comparisons we want to make. But we don't have to hold that data frame in memory on a single machine, even if this data set is many terabytes. The metadata of this data set is already huge, just describing all of these files, their file names and their buckets and everything. So we can create that as this big Dask data frame, and we can just kind of chunk our way through that. And we can load that up and actually join that with the text in the original data set. And all of this in Dask is lazy. So we end up with this kind of nice data frame where we have kind of the text of a document and a text of another document in a row. And we just have many, many rows. And these all just show all of the comparisons that we want to do, right, in order to see whether or not this is the same document. But this is, at this point, like a many terabyte data frame representing all of the data. We've kind of exploded it out and have lots of duplication in there, because you're comparing all the files with all the other files. But because all of this is lazy and because all of this is done in Dask, we don't have to worry about actually fitting that into memory. We just choose our chunk size to be something that will fit in memory, and we can have as many chunks as we want to work through this data set. And then we can actually kind of map over, do a row-wise operation over this data frame and do this comparison. So the way that the NeMo team has done this in Data Curator is by calculating the Jaccard similarity for each file. I would highly recommend going and reading the documentation and having a look at a demo YouTube video that someone from the QML team gave about how to actually do this. But these are using kind of standard pandas operations in order to do this computation. So if you imagine we're looking at one row and we just want to compare the text of one document with the text of another document, first thing we need to do is explode each document out into n-grams, right? You can see this representation on the left. We're just going to take this is like showing like a 5 gram, right? We take 5 characters in like a rolling window over the document. We're going to kind of explode out into that. And then we can compare the two documents to see what the overlap is, right? To see what common n-grams they have between them. So we can use the pandas explode operation, but because we've loaded this with Dask QDF, it's still the same pandas API that we know and love, but it's now like a chunked, distributed, accelerated variation of that same operation. We can then, on each row, use kind of standard pandas operations like join and group by and divide to compare these n-grams with each other, add them up, and work out what the Jaccard similarity is for each one. And this will give us a number between 0 and 1 to show us how similar each row is, right? Each document comparison. And then we can make some kind of decision about, what's our threshold for discarding duplicates? What do we consider a duplicate, and where do we kind of make the cut to throw things away? And we can see by running this on many machines using Dask to scale this out, and then using QDF and GPUs to accelerate this computation, we can look at an example like the 4.5 terabyte Red Pajama data set, running this through on like a CPU cluster with 20 nodes, and each node has got like a decent CPU with many, many cores. Running this through took 37 hours. Whereas just on 4 nodes with some GPUs in, this cut all the way down to 3 hours. Right, so this allows us to kind of do this pre-processing, ingest new data, train new models more quickly, update these models more easily by using GPUs to kind of accelerate some of this pre-processing. And it also, can provide like a cost saving as well, because you imagine 20 nodes, 20 high-end nodes rented on the cloud running for 37 hours is going to cost more than 4 GPU nodes. Even though the GPU nodes cost more per hour, you're not going to need anywhere near as many of them, and you're not going to need them for anywhere near as long. So by switching to GPU acceleration, we're still kind of just working in our standard pandas way, right? But we're kind of switching around from CPU to many CPU to many GPU to kind of cut down time and cut down cost of running through this. So that's kind of the end of what I wanted to show today. To leave you with these links, we have this blog post that the team, the NeMo team's written up about Data Curator and how it works and what it does, and all the other pieces of that pipeline, right? We've just focused in this talk on just doing fuzzy deduplication of the documents, but there's so many other stages of actually getting the data, doing all the transformations, other cleaning, other quality control, and things. So go and read the NeMo documentation. It's really interesting to see kind of how they've done that, and they link all the papers and things in there. And then also, if you want to learn more specifically about how we calculate the Jaccard similarity, then go and have a look at the Dask demo day session from earlier this year, where Jiwei showed that. And again, if you want to learn more about QDF and QDF pandas, go along to Ashwin's talk later on today. But that's it. Thank you very much for your time. We've got 5 minutes left, so if anybody has any questions, please go ahead and put them in the chat.
Thanks, Jacob. There's the first question from Ian. It should be showing up on the screen now.
Yeah, I can see it. I'll read them out and then ask them. So yeah, regarding QDF pandas, what sort of memory limits are we subject to? Does the data frame have to fit into the GPU's VRAM? Am I limited to 10 gigabyte data frames when I might have a 64 gigabyte system? Yeah, absolutely. So in that case, when we're just talking about, we're not worrying about Dask, we're just talking about accelerating pandas on a single machine, then yeah, QDF pandas will be limited by the memory of the GPU. If you want to add Dask to the mix, it can then swap data in and out and do kind of out of core stuff. So you're never actually bound by that limitation. But yeah, if you have 64 gig of RAM in a machine and a GPU, with only 10 gig of RAM, you'll be limited by that. But the nice thing about QDF pandas is it will try and accelerate things. And if it reaches the memory limit and blows up, it'll just say, okay, this isn't a GPU operation. It gets too big. I'm going to switch back to normal pandas. So to you, the user, you won't notice any difference. It's just that QDF pandas will speed things up where it can speed things up. And it's got a really nice little profiler in there. And it will show you like line by line in your code where, oh, it managed to run this on the GPU, or this fell back to CPU. But yeah, go along to Ashwin's talk and have a look if you want to learn more about that one. So the next question was, how reliable was your Jaccard document pair comparison measured to say cosine? Did you opt for Jaccard metric for better performance? So I honestly can't speak to this. This was something that was done by the NeMo team. I'm just kind of like showing An example that we've run at scale with RAPIDS and Dask, I would highly recommend you go and have a look at their documentation and read. They kind of reference a bunch of papers about what they measured and why they chose different approaches. So that would be the place to go and answer that question.